Hi, my name is Sarah Raker, and I'm the project manager for the Dinuba Wellfield RIFS project. I just wanted to let everyone know that Trilby's recording this meeting and she'll make it available on the website. She'll talk about that at the end of the meeting. Please note that funding for this project has been provided in full or part by Proposition 1. We're working under a grant agreement with the State Water Resources Control Board that is being managed by Robin. The content of this presentation does not necessarily reflect the views and policies of the foregoing, nor does mention of trade names or commercial products constitute endorsement or recommendation for use. So what we're going to talk about is, we'll give you an overview of the project in terms of what its major components are. We'll talk about the field sampling that we've completed since we met last. Mike will talk about the supply well profiling and some interesting results that we received. We'll talk about the refinement of our subsurface stratigraphy and the groundwater flow model. And then we'll talk about the major project deliverables and the due dates for those, the schedule and upcoming milestones, and then any questions you have. And you are welcome to ask questions during this presentation at any time. So let's discuss the goals and the benefits of this project. So the City of Dinuba received $1.75 million from Prop 1. And the purpose of the project is to develop potential implementation options to clean up or prevent the spread of non-point source pollutants in the City of Dinuba's municipal well fields. So we will identify the effective means to address nitrate, 1,2-dibromo-3-chloropropane or DBCP, 1,2,3-trichloropropane or TCP, which are widespread in the shallow aquifer in the region. And we are also going to identify projects which can be funded under future implementation grants to help assure a more secure and high quality water supply for the city. Here are some examples of potential implementation projects. We may modify well field operations, change the well field configuration, construct recharge projects that flush the aquifer system, and combine groundwater extraction for non-potable use, recharge to flush the aquifer, and source reduction and construction of new wells west of the city. So the benefits of this project are to improve the groundwater quality and supply resilience. We will also decrease treatment costs through these options. We would like to increase recharge for groundwater storage and demonstrate regional management strategies. So here is a really great cartoon of how we're doing all this work. We start with compiling and collecting data. We're collecting data that's been published and been available in the area from other experts and agencies. We're going to use that information to evaluate the data in a remedial investigation. We will develop a groundwater model and do engineering evaluation and evaluate screening criteria for the different options. And then after we grind it all up together in this meat grinder, we will have a feasibility study that presents the preferred implementation project. That's really the take home. The major project deliverables are a monitoring and reporting plan, which was submitted back in November, a remedial investigation feasibility study work plan, which was also submitted in November. And again, what we're working towards now is we're working on the remedial investigation report that will lead also to the contaminant fate and transport model memorandum. So the remedial investigation report will submit the data needed to conduct a fate and transport model. Results of the fate and transport model will be presented in the feasibility study report. So here we are on the field sampling. We've completed all the field sampling that's been, I guess, anticipated for the last year. And let's go to the next slide, and I'll show you. This will be familiar, I think, from the previous presentation. These little dots that are a little bit blurry, they represent the key wells that we're interested in for either collecting groundwater samples from them, doing well profiling to look at the chemistry of the water at different depths. There's also some information about the lithology, the screened interval, the total depth, water levels, pumping history, and water quality. And so that's a general overview of the wells that we're particularly interested in for the remedial investigation. The blue lines across the page show the water levels. We borrowed this from the Groundwater Sustainability Agency's latest publication for water levels. And so you can see that the groundwater is flowing essentially from sort of northeast to southwest. This slide shows you the key field operations or field activities that we conducted for the remedial investigation. The public water supply wells at the top, we sampled 6 of them and conducted we sampled wellhead and we conducted profiling. And over on the right side of the slide, you'll see the analytical methods or the analyses that we were targeting. And the COCs in this case are nitrate, DBCP, and TCP. On the Dinuba dry cleaners, we also sampled some wells there. There are sentinel wells that are located in the area of the city wells that we sampled. There are wells located near the wastewater reclamation facility. There's a test well located nearby the wastewater reclamation facility. And then there are 2 domestic wells that we sampled last month that were volunteers from folks that live just down gradient from the wastewater treatment plant. So I highlighted what we're going to show you are results of the public water supply wells that we did the profiling on, and then also just the domestic wells. And I think I'm going to hand it over to Mike Tietze to discuss the supply well profiling.
Thank you, Sarah. Yeah, and as Sarah mentioned, if you have questions, go ahead and either interrupt or raise your hand by clicking the raise your hand button, and we'll be happy to stop and answer them for you. So one of the key data collection efforts that we've implemented has been the profiling of these public supply wells. Ultimately, the project is intended to deliver cleaner water, make cleaner water available in the aquifer to the city's wells and other wells in the area, including domestic wells that might be completed in the upper part of the aquifer system. And in order to better understand how the water quality impacts to the shallow aquifer system from nitrate and from soil fumigant residuals, in order to better understand how those interact with the municipal supply wells in the area, we need to get an idea of how those wells interact with the aquifer system along their full screen interval. One of the challenges with these kinds of projects is that the wells tend to be screened at different depths. They tend to have long screen intervals, and they span aquifer zones with different water quality and interact with those zones differently. So what we did was we profiled 6 wells under ambient and under dynamic conditions. And what that means, ambient conditions is basically with the pump off, and dynamic conditions is with the pump on. And I'll explain how those two differ in a moment. So the 6 well locations that we profiled are located in the circled areas. So they're kind of from the central to the western and southwestern parts of the city, which is where most of the city's active wells are located. And you can see the different screen intervals from the wells. They range from relatively shallow wells. Number 7 is just 87 to 190 feet below groundwater, below ground surface, all the way to deeper wells like well 18, which is screened from 260 to 610 feet. And for all of them, we did video surveys, and we did ambient and dynamic profiles for 5 out of the 6. And then for well 15, we couldn't do a profile with the pump operating. So what we did instead was we did a profile with well 11, which was located nearby pumping, and with it not pumping, to assess how those wells affect each other and interfere with each other. And then the profiles consisted of flow profiles, which are taken using a special dye tracer test apparatus, which tells you where water flows into and out of the well when the pump is not operating, and where it flows into the well when it is operating. So how much water is coming from each layer. And then it also allows you to collect groundwater samples from different depths so that you can tell what the concentrations of nitrate, DBCP, and TCP are in the aquifer opposite the screen intervals of the wells, and at what rate those compounds are flowing into the well. So the way that we use the ambient well profile data, remember this is with the pump off. So we determine where groundwater flows into the well and where it flows out of the well. Very often with well fields like this, where wells are completed fairly deep under the ground, there will be a downward vertical flow in the aquifer, and that will be accentuated in a well, which is like an open borehole through which vertical flow can occur. So it's very common to get flow into the well in the shallow aquifer, and then out of the well in the deeper aquifer. And that can be a problem if there's bad water quality water that flows into the well in the shallow aquifer and flows out in the deep aquifer. It can degrade the deeper aquifer, or it can store the contaminated water in the deeper aquifer, so that when you first turn the well back on, you can get a spike in concentrations that you need to account for before you deliver water to your system. So we'll determine the groundwater flow within the well with the pump off, evaluate the vertical contaminant migration within the well. We'll use that information to validate the groundwater model that we're building. And is it able to show what we want it to show in terms of the vertical flow? Can it reproduce that, so that we can use the model to test if we can do something to improve that situation? So we'll use it to validate that aspect of the model. And then we'll assess how the wells interact within the well field. So especially with well number 15, we'll be able to see that, to validate how they actually interact. And then using the model, we'll be able to see that as well. The application of the dynamic, this with the pump on well profiles, we're able to determine the depth-specific contaminant concentrations and inflow into the well. The composite water quality that's coming out the top of the well, where is it derived from in terms of different depths in the aquifer? We'll estimate the wellhead concentrations for wells with long screen intervals. So what we learned from these 6 wells, we can apply to other wells for which we only have wellhead data, but the well has a very long screen interval. So we're able to determine to which aquifer strata the well concentration that we get at the wellhead, which strata does that apply to? So the results of the dynamic profiling will be used to evaluate the vertical distribution of flow along the well screens. So how much of the water that is being pumped by the well is coming from different aquifer layers. So we can validate the groundwater model and make sure that the groundwater model pumps from the same aquifer layers as the well does in reality. This slide shows several things. It's relatively busy. So I'm going to show you an example of what the well hydraulic profiling data looks like for one of the chemicals and for flow. We have complete reports for each of the 6 wells at this point, and those will be posted on the website when the RI becomes available, or if there's specific folks that have questions and they're curious, I mean, we can share information, along the way if folks are interested. You just need to put in a request to us, Trilby, or to Ishmael, and that contact information will be available at the end. So on the left-hand side, you see a square that's called DRM model layering. DRM stands for Dinuba Refined Model. So that's an area where we are establishing different model layers, or finer, more model layers, so that we can simulate vertical flow and interaction with wells. And each of the layers is between the green horizontal lines. And there's a total in this figure, I think there's probably about 10 of them there in the upper portion of the aquifer. And well 14 and 15 are shown there. And well 14, you see at 225 feet is the top of the screen and 620 feet is the bottom of the screen. And you can see that there's various different aquifer layers and model layers that correspond with that screen interval. The next box to the right is the well log. And there you can see the well casing going down to 225 feet in the screen interval. And then you can see the different sediment types, the different lithologies. So you can see where the clay, the sand, and the sand with clay is. So you can see where your most permeable zones are and which aquifer layers they correspond with. The next 2 boxes are the ambient profiles and the dynamic profiles. And the blue bars show the flow into or out of the well, and the orange bars show the concentration of TCP that correspond with those flows into or out of the well. So in the case of just the water flow, the blue bars, if they go to the right, that means flow into the well, and if they go to the left, it means flow out of the well. And so you can see that under non-pumping conditions, water flows into the well in the upper half of the aquifer system. There's kind of a tipping point where we see flow going in a couple of different directions in the central part of the well, and then in the bottom of the well, water flows out. And the TCP concentrations you can see in orange, and you probably see my face squinting at the screen here because I'm squinting at my own laptop. But you can see different concentrations flowing in from different depths. And that's of great interest to us because we want to be able to accurately simulate that and find out, where are the potential problem layers. And the specific problem layer for well number 14 appears to be primarily the second layer down that goes down to about 310 feet, 245 to 310 feet. We have the highest TCP concentration. And that well is currently being treated for TCP as a result. So this result helps us to know what happens if the well is not pumping and what depth intervals is most of the TCP coming from. The dynamic profile, you can see the blue bars, they're all now flowing into the well because the pump is turned on. So there's no vertical migration taking place through the well when the pump is turned on, and we can see that most of the water is being made in the third layer down in the screen interval from about 310 to about 330 feet below ground level. So where most of the water is coming in, the TCP concentration is a little bit lower. And the layer above it, where the TCP concentration is higher, there's less water flowing in from that depth. But there's a distribution there. So this information can be used to validate the model, see how the well behaves under different management and project scenarios, figure out what happens if we don't pump the well, and figure out how we might be able to modify the well in order to improve the water quality that's produced. So I know that that's a lot of information, but these profiles are very information rich. So the domestic well sampling, we had two residents south and southwest of the wastewater reclamation facility that allowed us to sample their domestic wells. These domestic wells are used for irrigation purposes only. They're completed to depths that are between 200 and 300 feet below ground level. And what we found was that the concentrations of groundwater coming out of those wells, the DBCP and TCP were not detected, and nitrate was detected at less than half of the drinking water standard. So good news for those residents. We do have some higher concentrations distributed throughout that area, but those particular wells and some of the other wells in the area, the concentrations were relatively low. So the refinement of the subsurface stratigraphy, one of the other ways that we are improving the available groundwater modeling is to collect data from well completion logs, drillers logs of the area, and using that to refine the permeability layering in the groundwater flow model, in that Dinuba refined model area. So the procedure, I'll just go through it briefly here. First, we acquire the well drillers logs, and we take that data, the lithologic data, and we put it into our project database, including information regarding the location of each driller's log. And there's a total of 401 of them that we analyzed here. The well completion intervals, well depths, and then a lithology table. What did the driller say were the sediments that were encountered at different depths? How permeable are they? And that data was standardized. This is using an approach that was developed by the USGS, first into standard soil classification, and then attributed to either a coarse or a fine texture, so basically sand or clay. And then that data was aggregated it was subdivided into 1 foot intervals, and then aggregated into 5 foot intervals. So, we looked at each 5 foot interval to figure out how much coarse and how much fine grained material was in it. And then we used a geostatistical method called kriging to determine what the distribution is of the coarse grained and the fine grained material in the aquifer system. We can provide more information about that procedure for folks who are interested. The outcome here is on the left-hand side, upper left-hand here, we have a map that shows the distribution of fine-grained to coarse-grained intervals. The western corner and the eastern corner, this is the orange there is just kind of an artifact at this point. We're going to clean that up and get the kriging to go all the way to the edges. But ignoring those corners, the orange is relatively fine-grained material, so a low percentage of coarse-grained material, and the green and blue is a greater thickness of coarse-grained material. So this is at one depth in the aquifer system, and you can see that the coarse-grained material becomes more prevalent as we move toward the west, away from the mountains and toward the Kings River. And that's consistent with what the city's finding has been, that they find that the aquifers are more productive on the west and southwest sides of the city. And in the what's called a fence diagram, the dark diagram with the cross sections and all the boring holes to the right, you can kind of see the same thing. You see that toward the left there's more blue layers, and toward the right, there's more lighter colored brown and orange layers, which mean they're finer grained. And then there's one on the bottom, there's this one cross section. Basically what we do is on about a 300-foot grid, we identify what the vertical and the horizontal distribution is of this material to, make our aquifer model layer cake, if you will. So the groundwater flow model development, this is a computer model of groundwater flow. So we had originally intended to use the AID model for folks who are knowledgeable regarding this under a current regulatory program called CV salts. The Alta Irrigation District area was selected to develop a model and to see, in theory, what could be done regarding salinity and nitrate in the aquifer system. The AID model, due to various different complications, was not able to be made available to us. So what we did was we extracted another model. I'll show you that in a subsequent slide. But first, the yellow outline is the original AID model boundary, Alta Irrigation District model boundary. The red is the actual Alta Irrigation District jurisdiction, and the blue is the Dinuba city water service area. So here's what we did. You can see in purple is the city of Dinuba water service area, and what we did was we used the United States Geological Survey's Central Valley hydrologic model, and we extracted a sub-regional model in the area that is in the black box. And the CVHM, Central Valley Hydrologic Model, is the same model that was used to develop the AID model. So we were able to basically, with a little bit of additional work, we were able to reproduce that and get it more to our specific objectives. And then within that model area, the green dashed model area around the Dinuba water service area, that's our Dinuba refined model. So as we get closer and closer to the area that we're most interested in, we refine our model in that area. And in the black box area, we basically use that more regional model to make sure that we have a smooth transition in terms of what are called boundary conditions that more detailed model interacts with. So we don't need to refine the whole model area. We really just need to refine what's in the green dashed box, but we need something in the black box in order for that model to behave properly. So the different steps for the modeling are, first is the model selection. And we talked about that we developed a new sub-regional model that was extracted from the USGS CVHM model. And that has, it's a model that runs up through 2003. We established the boundary conditions for that are supplied by our sub-regional model. And it covers most of the Kings River East Groundwater Sustainability Agency. And the hydrologic boundaries are informed by what's in that USGS model. We extracted the model and then we validated its performance. So basically what we did was we pulled the model out of CVHM and we reran it to make sure that we didn't screw anything up. And we found that it was virtually the same as the USGS model, so it behaved well. And then we updated the regional model, including updating the hydrology through 2015 with using data that was provided from another modeling effort by the Department of Water Resources. And then we are in the process of, I think at this point, we're virtually done testing and adjusting the model as needed. And then once we get that sub-regional model sufficiently, performing well enough, then we move to updating the local model and refining it. And then we want that local model to react with the regional model and with the aquifer in a predictable and accurate way. And once it's accurate enough, then we remove it from the sub-regional model and we can test our various different project alternatives using that model, see how effective they are. So this is another view of the sub-regional model. the gray slides the gray squares are bedrock areas. So those are inactive cells in the model. No groundwater flow takes place in the computer model in those. And you can see there's a little bedrock hill just to the northeast of the city of Dinuba there, where that's the case as well. And then the purple, pink slides, those are time varying specified head boundary conditions, and that's a fancy way of saying that the groundwater levels at those cells vary with time, and we know how they vary up to 2015, and so we simulate that. And there's a little inflow there on the northeast boundary that's also an inflow boundary into the model area. So this shows the model layering again. On the left-hand side, you see the CVHM model layering, and you can see some of those layers are pretty thick. They weren't thin enough to really assess the interaction of those long screen intervals with the municipal wells at the level of detail that we wanted to. So on the right there, you see that within the Dinuba refined model, you see that we created a lot of additional model layers in that upper 700 feet of the model domain. And this just shows you an example of some of the calibration, which is in progress. So this is the performance of the regional model. We're less concerned about that, so we're not paying as much attention to it, but we are paying attention to make sure that we get it, close enough. And we're not done with all of our tweaking yet, but this just shows you an example of, on the bottom, well FG 41513. You can see that the observed, or those are the measured groundwater levels, and the computed or model predicted groundwater levels line up really nicely for the most part. And honestly, with a computer model, this is about as good as it gets. And the upper one there, the FG 16101, that's not quite as good. So we're going to tweak that a little bit to get it to behave a little bit better. Some of it lines up, in general, what you want in that kind of a situation is you'd like the trends to be accurate, so you'd like to see increases where there's increases and decreases where there's decreases. So validation is in progress, and then there'll be a more rigorous, more formal calibration using groundwater levels within the DRM, within the refined model area that will happen in the future.
Okay, well, let's talk about what the next steps are and the opportunities for public involvement. Thank you. So we are working on the remedial investigation report, compiling the information that we presented today, along with a lot of data. And we're going to put it together and get it to the public for review end of this month or next month. So again, that's going to be the importance of presenting the information that's going to support the groundwater model and ultimately the feasibility study. The next deliverable is the groundwater modeling technical memorandum. That document will describe the methods that we use to do the modeling and the assumptions and input parameters that we use to calibrate or to create a model that's the best representation of the aquifer systems out there. The next document that we'll plan on providing is the draft feasibility study report. I just want to point out the box below that has gray, green, and blue. It shows you, thank you, Trilby, it shows you the individual tasks that we've been working on and where we are in the progress of those. You can see that the data visualization and analysis that Mike talked about and the conceptual site model, which is very important to incorporate all that data to allow us to then do the groundwater flow and transport model. We're getting close to completing the groundwater flow portion of the model and ultimately lead into the transport, which is looking at how the chemicals are moving in the water to help us figure out what the potential implementation projects could be. So on the blue, we'll be focusing on completing up the data visualization and conceptual model, putting it together in the RI report, then working on the tech memo under the groundwater transport model, and then ultimately into the feasibility study. One note, our original schedule was to have the project completed by July of 2021, and we have submitted a request for an extension to Robin. We needed to extend the schedule for a few factors, including we had difficulty accessing some of the wells that were designated for profiling, and we needed to do a special access to get into them, and in some cases lift the pump and shift it in order to conduct the profile. We also had limitations on access to some of the private wells that we wanted to sample. And then, as Mike mentioned, the Alta Irrigation District model that we originally intended to use was not available. So what we've done is made that recommendation to Robin, and I know that she's reviewing it at this time. What it will allow us to do is submit the feasibility study in by June or probably May, in order to potentially have time in order to get to the next grant solicitation. So that's going to work out. And Robin, if you would like to, you can give us an update on that, or we'll just let it go.
Hi, Sarah. So currently I haven't heard anything back from our program analysts, but I'm hoping I can certainly prompt them again to see where the process is at, but it does take a little bit of time.
Okay. And I think that's back to you, Trilby.
Yes, does anybody have any questions for Sarah or Mike before we move on to the housekeeping? All right, great. Well, you can always feel free, even if you think of any questions after the meeting, feel free to contact either Ishmael with the city. His email address is there. Myself, Mike, or Sarah. All four of our contact information is here on this slide. We also have a project webpage on the City of Dinuba's website. And there we have a video from the previous stakeholder meeting, if you weren't able to join us for that back in November. And we also have PDFs of the presentation. This presentation will be posted there, as well as previous meetings. And then we also have a neat video from a groundwater virtual site tour, groundwater sampling site tour that we did in February. So that video is posted there as well for the public and for stakeholders to take a look at. So please feel free to check that out. And then as the draft reports are ready for review, you guys will be notified by email, of course, so you'll be able to have an opportunity to review those and provide comments. And our next stakeholder advisory group meeting will be scheduled for June, so that'll be our third quarterly meeting. And thank you all for joining us today and for participating in this stakeholder advisory group. We truly appreciate it, and your feedback is always very important to us.
Let me just maybe add a couple of quick words. So where this is headed in the next meeting is, obviously, the results of the modeling will become available, but the most important thing will be starting to look at individual projects. What's feasible to do? How can we reasonably implement projects that will benefit water quality for domestic wells and for city wells in the area, and make those projects true multi-benefit projects that work and have the maximum benefit. So that's really what we want to look at. So we expect that during the next meeting, we will start to be able to unpack some of that. We won't have all the results yet, but we will have, what types of projects, where are they, and then, perhaps some preliminary ideas as to how they're performing by that time will be available. As information becomes available, it will be posted on the website. If you are signed up, you will be notified as different information becomes available. You'll be able to review and comment on the draft reports before they're finalized. And then lastly, for people who are interested, we will make ourselves available to talk to you about what we're doing if you have specific questions that you want to talk about, or specific ideas or things you want to better understand. This is a publicly funded project, and so we want to take seriously that we make this information available to the public so everyone can benefit from it. So that's all. Thank you very much.